Hello and welcome back to MathsBytes. You are probably pleased to see that we are finally ready to start to talk about the binary numbers. I promise to you, the wait had worth it, as understanding the concepts of the preliminary videos should help you better grasp the important concepts in this and subsequent videos. So in this video, we will discuss what binary numbers are. We will also talk about the binary place value system and the binary place value table, and we will look at how we can use notation to distinguish between binary and decimal numbers when necessary. First, let us remember what decimal numbers are. The decimal numbers are the ordinary numbers we use in everyday life, which have 10 digits, from 0, 1, 2, all the way to 9. Decimal means 10, which reflects the number of different digits we have in the system. Binary numbers are different. It helps knowing the meaning of bi as 2. So in the binary system, we only have 2 digits, 0 and 1. Here are some examples of binary numbers. 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1. I hope you have spotted that I have read these numbers out loud digit by digit, so we don't accidentally associate them with the decimal numbers. I suggest you also read them digit by digit, so you consciously separate binary numbers from decimal numbers. Next, I would like us to remember the decimal number system's definition, so we can modify it and build our binary number system definition. I'd like you to pause the video here and write down the definition of the decimal number system on a piece of paper. Here is the exact definition from 2 videos ago. If this is completely new to you, I suggest you watch my 2 videos about the decimal number system before continuing with this video, as I will be using many of the concepts we discussed in those videos. So, how could we modify this definition for the binary numbers? We know that the binary numbers use 2 digits, 0 and 1, and mixing up the digits in a number would create a different number, such as 1001 and 1100 are using the same digits but in different positions, so positions, place values are also important. Therefore, here is the definition for the binary number system. The binary number system is a base 2 positional number system. Now let us discuss what base 2 and what positional means for the binary numbers. First, do you remember what positional meant for the decimal number system? Please pause the video here and try to write down this idea. Positional means that if we place the same digits of a number into different positions or place values, they will represent a different number, as the values of the individual digits changed by placing them elsewhere. For example, 782 and 827 uses the same digits, but as the digits got placed to different positions, they represent a different number overall. Now, what does it mean for our binary number system? The basic principle is the same. So if we place different digits of the same number into different positions, the value of the number will change overall. The only difference is that we have a much smaller choice now, as we can only use 2 digits, 0 and 1. Here is a binary number, 1011. Now if we look at 1101, it also uses 3 ones and 1 0, but by placing the 0 at a different position, the overall value of the number has changed. 1011 and 1101 are 2 different numbers in binary. The definition of the binary number system has another part to it, in which the base is mentioned. Do you remember what the base is for the decimal number system? What did this base mean for the decimal numbers? Can you try to write it down? Again, pause the video here and try to come up with a sentence describing the role of the base in the decimal number system. The base for the decimal number system is 10. Base 10 in the decimal number system means that every digit has a place value position that is a power of 10. If you don't remember what the power means in mathematics, check out my video on indices, which is what powers are also called. Now, how can we apply this knowledge to the binary number system? Since the base of the binary number system is 2, it means that the place values in the binary number system must be powers of 2. I hope you now start to see the value of spending 2 videos on getting to understand the decimal number system and how it works. There was one more important concept we spent quite a bit of time on when discussing the decimal number system, and that was the decimal place value table. Can you pause the video here and try to draw out a version of the decimal place value table? Here's a version of the table. If you made some mistakes other than switching up the 2 heading rows, I suggest you watch my second video on the decimal number system to fully understand why those mistakes are problematic, and hopefully you won't make them again. How can we modify the decimal place value table so it can be used with binary numbers? Well, the important difference between decimal and binary numbers are the base and the digits. So if we swap the base 10 of the decimal numbers to 2 for the binary numbers, we will get the binary place value table. That's fine, but then you might ask, what are the actual values of these places? Well, we can apply our knowledge of indices here. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and so on. If this is confusing to you, please watch my video on indices. Now, do you remember what patterns did we spot in the decimal place value table when we looked at the column headings moving from right to left? The place values increased or decreased by a factor of 10 from place to place, and the indices were increasing or decreasing by 1. This depended on whether we were looking at the columns from right to left or left to right while we moved column by column. How does this compare with the binary place value table? Well, the indices still increase 1 by 1, but the numerical values are now doubling, getting twice bigger, column by column, when moving from right to left. What happens if we move from left to right? In the decimal place value table, the values get divided by 10 and the exponents decrease by 1. However, in the binary place value table, the values get halved while the exponents still decrease by 1 column by column. Here is a useful trick for you. When you want to write up the binary place value table quickly, start by writing out 1, then double this as you move further to the left, column by column. If you want to write out the exponent version 2, then write 2 into each column and start putting 0 into the exponent of the rightmost column, then keep increasing the exponent by 1 as you move further to the left. In the last part of this video, I would like us to discuss some important notation. To understand why this notation is important, here's a question for you. Is this number a binary number or a decimal number? The answer is we don't know. Just presenting this number like I just have, it could easily be 101, which is a binary number, or 101, which is a decimal number. Clearly, we need to make sure there is a way to distinguish between the binary numbers and the decimal numbers that just happen to be using only ones and zeros. After all, there are quite a few of these kinds of decimal numbers. So here's a common notation. To signal that a number is binary, we write a little 2 in the bottom right-hand corner of the number. To signal that a number is decimal, we write a little 10 in the bottom right-hand corner of the number. And you read it as the 101 for the binary and 101 for the decimal. Neither the 2 nor the 10 are integral parts of the number. It is simply an agreed notation to use when it is not clear if one means a binary or a decimal number. Neither is this notation specific for the decimal or binary numbers. There are as many number systems as many bases you care to choose, and this notation can be used for all of them, For example, if we were to put a little 3 into the bottom right-hand corner of the number, this would mean the number is base 3. A little 5 in the same place would mean the number is base 5. Many of these number bases are only interesting for mathematicians, but some of them are used in other fields of science. I will only use this notation when it is not clear from context if the number I use is binary or decimal. However, your textbook or lecture notes might have a different approach to this notation, so you should use what is expected of you by your lecturer or teacher. If you are ever in doubt, just use the little numbers in the bottom right corner, as it never hurts to be precise in mathematics. Now it is time to revise what we've done in this video. In this video, we have started to talk about the binary numbers. We have established that binary numbers are numbers that use 2 digits, 0 and 1. We have modified the decimal number system's definition for the binary number system, which states that the binary number system is a base 2 positional number system. Then we discussed that positional still means that different positions in the system carry different values, but in the case of the binary numbers, these values are all powers of 2, which is the base of the binary number system. We then modified the decimal place value table and built our binary place value table. And we also established that the patterns we spotted on the decimal place value table still hold for the binary place value table, with the modification that this time the place values get doubled when moving from right to left and get halved when moving from left to right. Finally, we have discussed that if it is not clear from the context whether a number is binary or decimal, we can use a lower index in the right-hand corner to specify the base number. For example, 1101 is binary, while 1101 is decimal. In the next video, we will use our newly acquired binary place value table and use it for converting binary numbers to decimal numbers. I hope you will join me next time too, but until then, keep learning one byte at a time.